So far we have discussed advanced solar cell concepts with contacts on both sides of the cell. We have discussed the passivated emitter and rear cells, the TOPCon technology and the silicon heterojunction technology. In this video we will move our focus to the advanced concepts for solar cells based on crystalline silicon that deviate from the standard solar cell design. These technologies are the metal wrap-through or MWT technology and the interdigitated back contactor technology abbreviated as IBC. Finally, a combination of the previously discussed HIT technology and IBC currently holds the record conversion efficiency for crystalline silicon solar cells. For a solar module based on standard crystalline silicon solar cells, the individual wafers that form the cells are connected in series by connecting the front metallization grid of one cell to the back contact of the next cell. This process is called contact tabbing. It is a time-consuming and precise processing step that in the past was frequently done by hand. As a consequence of these interconnections, is that the cells cannot be placed directly side by side, but that spacing is needed in between the cells. This area is accounted as loss when looking at the aperture area of the solar module. The metal wrap-through technology, in literature often abbreviated to MWT, prevents this loss in module area as it wraps the metal front contact through the base of each cell using a so-called via, and places both front and back contacts side by side on the back side of the cells. In this way, the electrons collected by the front emitter are transported to the back of the solar cell. Evidently, care must be taken that the via does not create a short circuit. Individual cells can now be placed much closer to each other. This image shows the SunWeb technology that was demonstrated some years ago by Schott Solar and Solon Solar. This technology can be recognized by its very special front contact design. The metal fingers are surrounding the wrap-through contacts in a very distinctive, almost flower-like pattern. Moving the front contacts to the rear of the cell thus offers an advantage on module level by reducing the area lost to contact tabbing. This idea can also be realized in a different way, by collecting both electrons and holes at the rear side of the cell instead of wrapping the front contact through the cell. The interdigitated back contacted solar cell has been another advanced design concept that has had major impact in the field. Also, this design features random texture and an anti-reflective coating at the front to reduce reflection and has surface passivation. This solar cell design eliminates shading losses at the front of the cell by placing all the contacts at the back, thereby increasing the light absorption significantly. Alternating highly doped N and P-type doped regions create small PN junctions at the back of the cell for efficient separation of charge carriers. Secondly, by using localized contact, the metal surface interface is reduced, resulting in a lower recombination loss. Similar to the HIT cell, the wafer base is N-type to increase the lifetime of holes. Instead of the previously mentioned back surface field, this cell design thus requires an N+ front surface field to push the minority holes towards the back. Efficiencies of up to 25.2% have been reported for the IBC solar cell. When we take a closer look at the metal grid at the back of the cell, here shown as a top view in the figure in the bottom left corner, it is clear that the cross-section of the metal contacts is much larger than the usual thin fingers of the front metallization grid. Resistance in the contacts is thereby minimized. We also observe that the P+ emitter region is wider than the N+ BSF region. This difference in coverage is required to reduce the effect of electrical shading. This effect results from the fact that minority holes generated above the BSF region need to be transported laterally in order to be collected by the emitter. By making the P+ emitter region wider than the BSF region, more efficient collection of the minority holes in the N-type wafer can be achieved. Having discussed both HIT and IBC, it turns out that a combination of these two concepts is possible, yielding an even higher conversion efficiency of 26.7% as presented by Konica Corporation in September 2017. The figure shown in this slide is presented in the latest article of Konica. Not all details are shown in this figure. However, it is clear that this design combines optimal collection of light at the front and reduced recombination losses at the back and front. It features front surface texturing with an anti-reflective coating, passivation on both sides of the wafer with hydrogenated amorphous silicon to create a heterojunction with a low surface recombination velocity and thus optimize VOC. All contacts are placed at the back to prevent shading at the front. Localized contacts are obtained by patterning the back with P-type and N-type amorphous silicon, and finally an N-type wafer base is used to increase the lifetime of holes. To conclude this video, we have seen that the metal wrap through technology can be implemented for module optimization by transporting the carriers collected at the front of the cells to the back. Using this design, the individual cells can be placed much closer to each other. The interdigitated back contact design also places all contacts at the back of the wafer and further increases light absorption by having no metallization at the front. In this design, all carriers are collected at the back. Finally, a combination of IBC and HIT yields the current record efficiency for a crystalline silicon solar cell of 26.7%. Recalling that the theoretical limit for the energy conversion efficiency of a single junction crystalline silicon solar cell is 29.4%, it becomes clear that PV researchers are getting closer to that limit.